to start.
Yep.
Yeah, so welcome on DataOps Poland, Brian. It's our guest today. It will be about the machine learning and the MinIO. So Brian, you are our star. Your time. So start the sharing the screen.
All right, thank you, sir. Nice to meet you all. My name is Brian Costa, and I am a business executive with MinIO. MinIO, you're seeing my screen, right?
Yeah, yes.
Perfect. MinIO is a 100% drop-in replacement for Amazon S3. That's its purpose. It runs anywhere. It runs on-prem, runs in any public cloud, runs on Kubernetes, runs on bare metal, runs in air-gapped environments. And the way I got here is kind of circuitous. I started as an engineer developing code for Hewlett-Packard, and I was in Unix development labs way back in the early 90s. So I go back a ways, and I go that deep. I was working with neural networks from about 1990, specifically in foreign exchange, but also in other areas of finance. I love them. I built them by hand back before there was an internet. And they're really cool, and they've always been my passion. And these two things come together because what I'm seeing now is that if you're storing data for, we'll call it big data, but if you're just storing data to do training on or to do execution on, it used to be that you would load MySQL or Postgres or MariaDB, or if you were in an enterprise, you would store it in Oracle. And if not, you would have it in CSVs on the file system. And obviously CSVs are very inefficient. And when I've tried to do work like this with MySQL, for instance, I would always sigh when I had to set up the database. It requires another person in my world, because if my focus is on building algorithms and I'm really focused on that, I have limited brain cells. I don't have the ability to also manage the database. And so what I found is that object storage generally provides another alternative. And so we're going to do machine learning with H2O, which is a machine learning platform, leveraging MinIO, which is object storage, and some relatively new file formats that are much more efficient than CSV. And the area we're going to work on is foreign exchange with statistical arbitrage. And statistical arbitrage is the notion that there is a somewhat stable relationship between two instruments, the pricing of two instruments. And if there is a deviation from that underlying relationship, then we assume it will revert back to that relationship sometime in the future. And that deviation provides an opportunity to take a position in those assets and potentially make money. Stat-arb is old, right? And it can be applied to virtually any instruments where you find a relationship between the price movements of those instruments. It's also fairly simple. In the past, it's been done primarily with subtraction, right? Or some variation of a fixed equation, where asset 2's price is equal to some equation, that involves asset 1. But it's very fixed. More recently, we can apply machine learning to learn the relationship between the assets, and that's what I'm going to do here. So I guess a caveat, this is for educational purposes. You probably won't make money doing this, and there are a lot of ways to investigate to make it better. I threw this together in a few days, and it's not great, but it lays out how to approach it, and we do see some value. I did see some value to it. So the pipeline for the machine learning aspect of this is I take in data, currency data from TraderMade, which is available for free. They have limitations, but you can get data that works for this purpose. I bring those in R. I create data frames in R. I like R as a statistical language. I land those in MinIO in the form of Parquet files. Parquet files, as you're probably aware, are tabular in nature. They have columns, they have rows, but they're much more efficient than CSV, and they allow you to do things like partition, which is, the file equivalent of setting up an index on one of the columns. So I land these files in Parquet format within MinIO object storage, partitioned by date, because typically you're retrieving by date when you're dealing with financial data. MinIO has a feature called Lambda Compute, which is the ability to trigger code when there's a change in one of the storage buckets. So when a file arrives, one of these data frames is stored, you can trigger arbitrary code to run it. And we're ultimately going to run H2O's AutoML capabilities to train a deep learning model to predict the relationship between two currency pairs. So the process flow looks roughly like this. The currencies come in, Parquet format, stored in a bucket, which I've called Apache Arrow for because I'm not that creative. Then using H2O to train the models and storing the models in another bucket called bin models. If in your enterprise you have a model repository, you can store the models there certainly, but sticking them in a bucket and writing some data, some metadata about the models is often good enough if you're rolling this at home yourself or whatever. That model is then used to try and discern the relationship between the two currency pairs. And when the underlying relationship between the currency pairs deviates from its historical norm, we see that as an opportunity to trade, to take a position in these assets and potentially make some money. It's a non-stationary problem in the sense that the relationship of the underlying currency pairs changes over time, and you've got to accommodate that. For this, I use the previous 6 months from January through the end of May for training, and then I apply it to June through the end of September as an example. The currency data coming from TraderMade looks something like this, and I'm using daily data. Obviously, if you were really trying to make money with this, you would use a finer granularity. But for the purposes of this demo, it's the same regardless of what granularity you use. And again, the data includes a quote date. It's the date for which this row holds. And it has an open, high, low, close structure for the daily window. Generally, when you're dealing with financial data that has open, high, low, close, or is what's called bar format, you average the open, the high, and the low as a single data point representing that time period. So I create a quotes.average within the data frame, which is just the average of open, high, low. The close of any given period is the open for the next period, so you don't include it in the average typically. And this gives me a single data point for each day. Now, when dealing with foreign exchange, that is an average of an average of an average. So it's not very accurate, and doing this much averaging hurts the returns. It hurts the algorithm. But again, it gives, from an explanation standpoint, it makes it easier to explain what's going on. Retrieving the data from within R is fairly easy if you're using the Arrow package and the data is going to be stored in Parquet format. In the code, and I'll go through the code after the slides, I create a function, download CCY, data frames, DFs, specify a couple of currencies, a start date and an end date, and that function returns some data frames. The function does nothing more than call a data-related function in the bottom block, gets the data frames, then writes those as Parquet files out to object storage. And these blocks are really everything that's required for retrieving and storing the data. So as a single developer, I can wrap my head around this, and I don't need additional data structures or friends to help me, people to help me with wrangling or managing the data. It's very easy. And again, the advantage to these formats, and there's a lot of newer tabular formats, is that they provide a compressed and efficient way to effectively index the data. In my case, I partitioned it by date because I'm going to select effectively based on date. And when you do that, a number of files are created. These are the buckets within MinIO, standard S3 buckets. And then the files are stored within subdirectories or prefixes underneath that bucket. And you can't really see the one on the left, but on the right, these are the files partitioned by quotes.date, which is a column within the data. So if I want to select all columns for a given date, only this individual file needs to be read back. I don't need to read the whole thing and sequentially walk through the dates column to find the rows I'm interested in. I can partition by multiple columns, and it'll build the appropriate hierarchy, and it's a very efficient way to do it without having an underlying database to do that work. As an aside, we are seeing that many database platforms support these tabular file open standards as external tables. So if you have, for instance, Microsoft SQL, you can use one of these, a number of these formats of files and declare them as external tables, and then have the full power of SQL Server against that external table, which again is nothing more than one of these file formats. So the first experiment is we're simply going to subtract. We're going to subtract one currency pair from the other currency pair and assume that that relationship, that difference, is the underlying relationship that is somewhat stable. And if we deviate from the history on that, we can take a position in these assets and potentially profit. So in order to keep it from being purely stationary, I'm using a 10-day mean and standard deviation rolling window for the difference between these currency pairs. We look at that in terms of standard deviations from that mean. And this data is not normally distributed. It's not a Gaussian distribution. So the idea of a standard deviation is not accurate, but it gives us a way to talk about distance from the mean. And if the current quote for that day is significantly far from the mean of the preceding 10 days, then it's potentially an opportunity to trade. So I set up a system to identify those outliers, if you will, or where it's deviated from the relationship, and to take a position in them and to trade effectively. And then I ran it from June through the end of September. And at the end of September, I liquidated all the currencies back to USD and took a look at the profit or loss. So this gives you an idea. And again, I tried one currency. I tried, one experiment effectively here, which were two currencies, right, against each other for this period of time, and that's it. So over that time, from June 1st to September 30th, the S&P 500 lost 21%. I tried this system, which was taking some starting balance in USD and purchasing the currencies that I would need to trade and performing no trades and then liquidating at the end. And that's our null hypothesis. The idea that you would set up the system, you would not trade at all, no indications to trade, no trading, and then liquidate at the end. So what happens over those months? And the system loses 8.2%. And that's really our baseline, right? That's our null hypothesis for these experiments, and that's what we have to beat. using the 10-day rolling mean and standard deviation, and then trading outside of these boundaries that you see the red hash marks, we still lost money, but we lost less. The performance was negative 7.5%. These are not annualized figures or compound annual growth rate figures. These are the simple return over that 3-month period for each of these. So using a system that is based upon the mean and standard deviation in trading when the currencies are outside the bounds does perform better. So that was kind of interesting. And of course, there's a lot of infrastructure that goes into setting it up. The second experiment is use H2O's AutoML capabilities to try and learn the relationship between these currencies, train it on the data from the first half of the year, so January 1st through the end of May, and then apply the model that is derived to the third quarter, right, June 1st through the end of September. This is fairly static, right? I'm training it a full half year ahead of time, and we're applying it for a full 3 months. If you were building this as a production system, you'd probably train on more recent data, or at least weight the data that is more recent to be of greater significance, and you'd probably retrain more frequently. But the idea of training on history still holds. So in R, you load the H2O package, which again, fairly easy, and then you can easily set up AutoML. And I'm not going to dig into the parameters here, other than to say this is a fairly short run, right? Run this for a minute, basically, and figure out the best model from those that you run, and let me know what that is. In a production environment, you'd run it a lot longer, and you would certainly work to investigate the parameters of how you can tune the AutoML to achieve better results. But once again, the approach still just works. So the model that's returned gets saved, and we're saving it again to MinIO S3 storage. It could be to a model repository if you have one, but S3 storage, and then setting up some metadata about the model, what it was trained on, what its performance was, when it was trained, etc., works. These are the results for the cross-validation of the model's training for the data that I had. They're not terrible, right? I mean, you can pick any one of these that is your favorite stat. R squared is interesting, right? We captured 84% of the variation. That doesn't seem random. That's okay. And the model that was chosen after, and I believe it tried 10 models, was a GLM variation with some tuning. As an aside, again, I used to code neural networks in C from scratch from the textbooks way back when, and you had to write everything yourself. There was no Python, there was no TensorFlow, there was no internet. And platforms have gotten so easy. And when I look at these, I'm simply amazed. And it's also kind of become true that any platform can do anything. So you're not limited to using only H2O or using only TensorFlow or using only PyTorch, because the platforms all have similar features, or there are libraries available to give you the functionality you need in almost any platform. I like R, I like H2O. It's simple and it works for investigation. If you're moving this to production, once you determine how to derive the relationship and all the steps you need to actually execute this, you might recode it. You might recode it in whatever language and using whatever platform you have support for in the enterprise. But as an individual doing investigation, these tools work pretty well. So when I run this model, and again, set up some thresholds around the mean and trade when the relationship deviates from what is expected based on the model, we do a little better, right? Again, the null hypothesis for this trading system is losing 8.2%. And based on, trading based on the indicators derived from applying the model, we only lose 6.3%. So, the upshot is I can't recommend you use this for your retirement funds, at least not in the not from June to September of this year. But relative to the S&P 500, it's really not bad. I'm going to stop here for questions about this, and then I'm going to walk through code if you are interested. So, any questions at a high level?
I would have actually a question. In case of the platform, what was why have you chosen the H2O or instead of any other platform? Because there are like dozens, maybe not dozens, but let's 30 platforms like Neptune, Valohai, DataIQ or on any other. So do you have any recommendations on that?
Well, I mean, my recommendations are only from my own experience. I haven't tried all of them, obviously, but I got involved with H2O maybe 5 years ago and started using it. It's built in Java, and it's a single binary. So you download it and you stick it in a directory, and you start it up with a command line that specifies some configuration, and it runs, and it just runs. It has the ability to form clusters. So if you have multiple machines running it, you tell them about each other, they find each other. And it has the ability to run larger models across those machines. So it scales with adding machines. And I found it just works, quite honestly. I found it easy to use. I like R as a statistical language. Again, my background is procedural languages, so C and Java and Go. But for vectorized work, for statistical work, I like R. And R's interface to H2O, again, just kind of works. You make calls and it works. And that's really the reason I use it. But, I recommend it, but I haven't done an investigation of all the platforms that are available. And to your point, there's a never-ending list of them now.
Yeah, so for example, I was using MLflow with weights and the biases. So I think this is a huge benefit of having just a simple binary to run it, because very often the tools are not integrated properly, and it's really hard to set up everything properly to catch the metrics and more. So yeah, I didn't know that H2O is just a single binary. Maybe I need to try it actually. So
yeah, so at MinIO, we help customers set up all kinds of use cases. And one of them that we're working with now is TensorFlow and Kubeflow on OpenShift using MinIO. And to your point, the configuration is a nightmare. And it's a lot of time spent dealing with infrastructure and getting it working. Forget about time to actually build a model or investigate data. You're spending all your time making it work at all. I don't have patience for that personally. And to your point, that's why I use this, because for me at least, it just works.
yeah, I got same issue with Kubeflow. The setting up was just a nightmare.
Yeah. So although it's cool and everyone's using it now, it is a bit of a nightmare.
Okay, we've got one question. Can MinIO Lambda start any code like OCR?
Yeah. So the way that MinIO Lambda works is it sends an event, and it's a JSON event to any endpoint you want. So you can send this over Kafka or over any other FIFO, or you can send it to a webhook. And when that event is received, the information inside it indicates what bucket changed and what changed within that bucket. So yeah, so you can trigger OCR. I have triggered anomaly detection on log files, for instance. So we have a log file collection process that brings the raw log files into a bucket, and a sort of inbound bucket. And then Lambda notification kicks off transformation of those raw log files into data frames, and goes out and manipulates the data frames, and then ultimately identifies the anomalies, exports that out to SQL Server. And that's all triggered by Lambda notification. You can trigger virtually anything. All right, anything else? Can you check only some part of big files? So that's the advantage of Parquet, for instance. The Parquet format allows you to partition, and partition is effectively building an index. I think this slide. So I read in this currency data, and I chose to partition it based on date. And within the arrow bucket, what was stored is a number of smaller files underneath the currency pair that I downloaded and partitioned. And these are chunks, and they are effectively, each one is a row of the data that I brought down, where the date is equal to whatever the name on this date is. So if you think conceptually how a database index is built, it's similar. You have metadata that indicates where given columns are, or sorry, given rows are based upon their column value. And that metadata allows you to efficiently read subsets of the file. The cost, of course, is you have to build the index every time you update or alter the file. So there's a cost on the write side, but there are advantages on the read side. So if your use case is write once, read many, then building indexes makes sense. If your use case is write once and never read because it's archive, you probably don't want to bother building indexes. You don't need them. You're not really reading. And if you build too many indexes, you do a write once, read many, and you've indexed everything, then that write, or I should say write infrequently, that write becomes very expensive to maintain the indexes. And if you're not actually using those indexes to query against, then that's CPU usage that isn't really valuable. Partitioning is similar. Like, I can partition on every column within this data that I've brought down, but if I know I'm only querying by date, then those, all of the chunking up of the file by the values in each column doesn't really help me, and it creates a bit of a mess. The advantage here, and I think I mentioned it, but let me drive it home, is that the data formats, these open table data formats, and this includes Iceberg and Hootie and Orc and Parquet and a bunch of others that are relatively new. They mean that a database application can then focus on providing database functionality and not worry about the proprietary data format that it uses to store the underlying data. It can leverage one of these open formats. And that's the direction that we're seeing products, again, like SQL Server or Snowflake move in. They are providing support for these open data format files to be used as what they call external tables. They ingest the file, they may partition it to create effectively an index, and then you can perform joins and selects across tables or whatever you need to do within that application, within SQL Server, where the data for this table at least is stored in an open table format, not in the SQL Server proprietary format. That was kind of rambling, but yes, you can check only some parts of big files. That's a yes on that one. Anything else? Okay, I'm gonna this last slide are just some links, and I'll provide this slide deck, but you know, so you have access to these. I'll provide the slide deck. Okay, so you know, how much of a nightmare was this code, right? Let's talk through that. So if I look at the files, you know, I've got less than a dozen files here, and they're sort of laid out fairly naively and as you would expect, right? There's some functions related to getting the data from TraderMade and returning it. And, you know, to get this data, it's less than 50 lines, basically. I created a function called get the CCY rates, get the CCY time series. And this is code taken almost directly from TraderMade's example. So I didn't have to fight my way through this, pretty easy. And it returns a data frame. So that raw data frame goes to another set of functions, typically, which manipulate it in some way. Here we can create, we can load currencies into data frames or create a joint data frame from a couple of currencies, or create a lagged data frame for the machine learning aspects of this. And all the code here, you know, about 100 lines. So compared to other languages, you know, R is pretty efficient. This is why I tend to like it. So now we have the ability conceptually to get data frames of currency information. So what do we do with them? Well, I've got a main for the absolute use case, the one where we are subtracting. We obviously make calls against those functions to get the data frames with the currencies, and we build a joint data frame, and we set up some thresholds, do some charting, and then eventually we test, right? We go through and determine which days should we buy and which days should we sell, and what should we buy and what should we sell. And then once that data frame is created, we run that through some test actions to derive the return. And, you know, there's a lot of nuances here. When you're dealing in currencies like, you know, Euro, New Zealand dollar, for instance, which is one of the currencies, in order to be able to sell either Euro or New Zealand dollars, I have to own some. So when we come into the testing framework, I have to understand what's my starting balance and what is it in. For me, I started, you know, you can set it arbitrarily. I set it for 10,000 bucks of USD, US dollars, and then chunk up, or I should say purchase some amount of each of the currencies that I may potentially have to sell. Can't sell what you don't own, right? This doesn't allow short selling. So spend that 10,000 bucks and shift it into the currencies you're interested in. Determine the size of the trades you're going to do. Here, again, it's very static. I just took whatever the balance in each currency and divided by 20. I'm assuming for the period under test, I'm just going to have 20 trades and each one's going to be the same size. There's a lot more intelligence that could be introduced here. For instance, if you're trading on a point that is further from the mean, further from the statistical relationship that you believe will revert, you could trade more if you thought that was appropriate. So you could adjust the trade size based upon how far from the relationship the current day is. You could dynamically convert USD into whatever currency you need. You know, I do it statically here, and what that means is if I run out of a currency when I'm in the middle of my trading run, I don't trade that currency because I don't have any. Obviously, something much smarter would be used where potentially the balances were adjusted dynamically. As if you ran low in euro, you would buy more euro. And then based upon the actions, which are, you know, the data points at which we deviate from the relationship, we would buy and sell the appropriate currencies in the appropriate amounts. And that's just a bunch of if logic, right? And it's a little tedious because every buy and sell is really 2 items. But and then at the end, we unwind all this and accumulate the balance back in US dollars to figure out what was our, you know, we started with 10,000. What did we end up with at the end of this run? What did we end up with in US dollars so that we can compute the return? And, you know, again, about 130 lines. Very simple, very basic. Lots of areas where you can enhance this. Lots of directions you can take it in, but you get the idea. Start with the balance, acquire some of the currencies you hope to trade when appropriate. When you're all done, liquidate or unwind it back into your base currency, USD in my case, and then figure out if you made money or not. And that's how the returns are calculated. For, again, going back to the absolute, that's kind of it, right? You maintain the rolling window, the 10-day mean and standard deviation, and when you are far from the mean, or when you violate or cross the threshold, you actually set up a trade and you execute. For the machine learning model, which is a little more sophisticated, it's similar in nature. This is the main for the machine learning model, and that you identify your currencies, start date, end date, blah, blah, blah. Get the data, blah, blah, blah. Build some training data. The training data is for January 1st through the end of May. And they are, each training instance is 10 days worth of difference between the currencies. The most recent 10 days difference between the currencies from the date of that training instance. So you aggregate all those together and that becomes your training data. Using 6 months is a lot, right? I mean, typically you would use a shorter window. You would also be aware of whether there were government actions or central bank actions that would change how you perceive a given currency. This modeling that I've done assumes that there really aren't any exogenous actions, right? It's all endogenous. The model controls it, or I should say the economy controls it. The Fed doesn't step in and adjust interest rates, which changes currency values. And then you train the model, right? And with H2O in R, if I go into the ML functions and look at training the model, it's pretty painless, right? I get a training data frame coming in that is all set up to train. I split it for training and testing, 60-40 in this case. It could be anything. I identify what is the Y value that we hope to predict and what are the predictors. And then I pass it all into a model. And the model is, I pass it into an auto ML call. The auto ML call is this, which I had on the, boom, that might be a little better, which I had on the slide, right? You pass in the identified Y value, the identified predictors, the training data frame, a test set for determining the leaderboard of the various models that it's going to run or try, a time limit for each of them, and I set a seed so that it's reproducible. And then I take out the model that is the best, the leader. In the comment here is something similar, but using just a straight deep learning model instead of trying various models. H2O supports all kinds of models. There are more than I'm aware of, so you can dig through that. And then ultimately that model is saved, in this case, back to S3 storage, but it could be into a model repository if you had something like that configured. Running the model is similar. You pass in the model, you pass in the data frame that you want to do predictions, you want to use for predictions, and you make a single call, H2O.predict, passing in the model and the hex value of the data frame, and it returns the predictions back out. So the entire ML code for this thing, if you're using the H2O package, again, it's under 60 lines here, and there's a lot of white space. Pretty painless.
One question to the model, if I may.
Yes.
Basically, H2O AutoML would try to tune your model or find an optimal architecture, possibly. But I wondered about the 60 seconds were set. This is maximum time for model for architecture or for model tuning, or
I believe it's for running. Sorry, for training, I should say. So yeah, it'll pick, I believe, 5 families, and I could be wrong on this. I'm kind of making this up, but I believe it picks some number of families of models, and then does a grid search on parameters that are appropriate for each of those families, and starts some number of models of each of them in parallel, and then lets them run a while, in this case, I believe 60 seconds, and then determines which is performing best and tosses out the others. So what's interesting is if you've done some modeling in the past, you typically look at the error rates on a verification set, right, or a validation set, not on the training set itself, because you want to evaluate the error on unseen data. And if you do that periodically to see how it's doing, you end up with a curve over time. And that curve over time isn't really predictable, right? Your error may shrink very dramatically in the early stages and then flatten out and never get better than, X, whatever. And a different model with different tuning parameters may take a less dramatic drop in the beginning and may take, let's say a more linear decrease in error, but ultimately arrive at training parameters that give it validation code, validation error or verification error that's lower. So limiting it as far as time is sometimes a problem. But what that would mean, if you said, okay, so we should let them all run until they converge, is it would take a long time, but you'll end up with identifying a better model if you do allow that to happen.
Yeah, I was actually thinking if you try to run it for longer time, because for example, hyperparameter tuning may take hours, even longer sometimes, and this is very expensive usually. So 60 seconds for small projects is very well. I think it should figure out at least some of the good parameters. But I wonder if you could try, for example, for an hour. If it would change the outcome so very much or not really.
Well, I suspect it would change it a lot. The first work I ever did with foreign exchange was in 1991, and I trained on to predict currency movements back before the euro. So there were 20 currencies I was looking at, and I was looking at 20 years data. And each of those models trained for 30 days, to your point, right? A hell of a lot more than 60 seconds. And so you save the model intermittently because the machines would crash, and then you come back up and pick up the half-trained model and keep going. But it can take a long time because, again, the curve of the error is not linear and it's not predictable. So you don't know early on which one will be the best. To your point, I think more time is needed, and you'll see a significant improvement.
Yeah, thank you.
We have like 8 minutes left or 7 minutes left. Any questions? I can keep yapping as long as you want me to. All right, advantages of doing this with Forex versus equities, because you can certainly execute statistical arbitrage on equities. You would execute it on stocks, on companies within the same industry. So you could do car companies because they're all roughly the same size and they compete within the same industry, and there should be a relationship between them. The cost of steel would affect all of them similarly, the cost of rubber, the cost of labor. So there should be an underlying relationship between those assets, those equities. And it works. That art works for that, except equities are subject to corporate actions. A given company may decide to split the stock or not split the stock, or pay a do a shareholder compensation, a buyback of some sort, which is obviously an external event. It's not part of the economics of that industry. It's an external decision the corporation made that would affect the prices that you're using. So that makes equities harder to work with. Foreign exchange doesn't have that issue, but it has the issue of there is no central market for trading foreign exchange. There's several markets. So the prices that you're working with may not reflect what you can actually trade at. That's a concern. And foreign exchange rates are the rate between two instruments. It's the rate between, for instance, euro and New Zealand dollar. So if that number is too high, what do? Well, you've got to sell euro and buy New Zealand dollar. It becomes more complicated in the form of what the transactions actually are. You can, you would buy or sell euro NZD, but effectively you are trading two currencies. I don't know. Where do you want me to go? What do you want to know? How can I help you? Was this useful?